In this video, we're going to look at limiting reactants and percent yield. The two pieces that we're going to spend some time on in this section is identifying which chemical is actually going to run out first. The premise behind that is a reaction is not going to go forever. Reaction is going to stop when one of the reactants runs out. So if we're given a situation, we've got to be able to identify which chemical runs out first, and then from that helps us to determine a whole bunch of other things. Second thing we're going to talk about is percent yield, which basically leads to how efficient a reaction is. Okay, and is it a good reaction or not in terms of what's produced? So limiting an excess reactant, pretty simple. If we think about ingredients, you're making something. That's what we want to think about, limiting an excess reactant. So we kind of see what those are, and we'll get into some of those examples here in a little bit. Then you've got yield. Theoretical yield, actual yield, percent yield. So our goal is here to obviously count or calculate a percentage, how good was the reaction. But to be able to do that, we need to know what should have been or could have been produced compared to what actually happened. So it'd be like, what's the textbook say we should make? And then we actually go to the lab stations and make the chemical. Did we make what we should have made? Okay, did we make more than what we should have, which is impossible? If we made less than what we should have, why did we make less? What happened? What did we miss? All right, so we're going to spend some time on that. These really aren't new calculations, the yield stuff. Limiting excess reactant, those aren't new calculations either. We are just going to be manipulating moles, mass, mole ratios. That's all we're manipulating. We're just going to use them different ways. All right, so here's an example. Now, depending on when you're watching this might be in the morning, lunchtime, dinner time, late at night, might make you hungry. So imagine you're working at whatever hamburger place, McDonald's, Wendy's, Burger King, you name it. And let's say you're taking inventory and you got to make cheeseburgers. How many could you make versus how many do you actually make given your inventory? So let's say your piece of, your hamburger, whatever special hamburger it has obviously a bun, 2 pieces, 7 pieces of cheese, and 3 pieces of meat, 3 pieces of hamburger. And in your inventory, that's how much you have available. So the first thing you got to decide is, how many cheeseburgers can I make given that inventory and given how many, what's going to be in each cheeseburger? Well, I think, after a few seconds, you can kind of recognize what's available, okay, versus what could I make. So based upon your inventory of the bread, the cheese, and the meat, that's what you could make. So what I want you to think of the bun, the cheese, and the meat as reactants, and the cheeseburger is the product. So how many products could we make given these 3 reactants? And you notice we're going to make a different amount. Well, our problem is we're not going to make cheeseburgers forever. At some point, we're going to run out of material. When are we going to run out of material? We're going to run out of material after we make the 99th cheeseburger. We will not be able to make 100 cheeseburgers because we're going to run out of cheese first. Okay? So what we want to talk about then is how do we kind of calculate this? And this is working towards the chemistry piece. So again, bun, cheese, meat, that's how many pieces available. That's how many we could make. That's our theoretical yield. That's what we could make. In reality, we're only going to make 99 cheeseburgers. So how much of the ingredients are we going to use up or consume? Given that we'll make 99 cheeseburgers, we're going to consume 198 pieces of bread or bun, 693 pieces of cheese. So we're going to run out, every piece of cheese gone, no leftover pieces, and then 297 pieces of meat. So we're going to have a limiting reactant. The cheese runs out first, but we're also going to have leftover. Right? We're going to have some leftover bread. We're going to have some leftover meat. These are what we call excess reactants. We have extra chemical left over. So as we're looking at this, we want to now just apply this to a chemical reaction. Instead of bun, cheese, and meat, we're going to have sodium chloride, silver nitrate, and carbon dioxide. And then instead of producing a cheeseburger, we're going to produce sodium nitrate, silver chloride, and hydrogen gas. The concept still applies. Right? So here's what I want to think about when we're talking about this. There's kind of a simple way to do the calculation, but it's a little bit longer. And then there's also a shorter way, but it's not a harder calculation, but we just got to keep it straight. It might be a little confusing. So here's what you do. You basically begin with both reactants, and you solve for any products that are possible. The reactant that produces the least amount of product is the limiting reactant. The reactant that produces the most amount of product is the excess reactant. Now, the thing you got to remember about that is the excess reactant won't actually produce that amount, because once the limiting reactant will run out, the reaction is going to stop. So this just helps us identify what's going to be produced, how much, which one's going to run out first, and which one's going to have a leftover amount. All right, so what I want to do is just look at a simple example here. And this is what's the sample problem on page 313. Here's the thing we always got to do, and this is important. We always have to compare moles if we try to figure out what's going to run out first. We cannot look at grams. Okay, so the limiting reactant is always going to determine the product. That's the second thing we got to remember. Now, before you do a calculation, look. You might be able to see which one runs out first before you actually do the calculation. If we look at the reaction here, SiO2 plus HF, like SiF4 and H2O. The ratio between SiO2 to HF is 1 to 4. I need 4 times more HF than I do SiO2 to make the reaction work. So now, what I have are just 4 different examples. So this is saying what if. So what if, in the first example, I had 7.92 moles of SiO2 and I have 14.97 moles of HF. I'm asking what is the limiting reactant. So I'm going to go, what's the limiting reactant? What's the excess reactant? And the reaction says I need to have 4 times more HF than SiO2. Let's look at the numbers. Do I have 4 times more available? No, I don't even have twice as much. So do I have enough HF knowing I need to have 4 times more? The answer is no. So what chemical will run out first? HF. What chemical will I have extra left over? SiO2. Another way to say it is I need 1/4 as much SiO2. I got a lot more than 1/4. Second example. I have 2.97 moles of SiO2, 12.4 moles of HF. Do I have 4 times more HF? Well, if I call that 3, and I call this just a little bit greater than 12, 3 to just over 12, yeah, actually I've got a slightly more than 4 times greater. So if I've got slightly more than 4 times greater of HF, that's now the excess reactant, and SiO2 is the limiting. Third example, still the 1 to 4 ratio. Do I have 4 times more HF than SiO2? Obviously, no. I don't even have equal amounts. So we're back to HF being the limiting reactant and SiO2 being the excess. The last example, 4 grams and 16 grams. Oh, yeah, I got 4 times more. It's going to run out. Stop. Can't do it. Grams, grams. We have no idea, because the only way we can compare is if we first change them into moles. So if we were to change these into moles, times 1 over molar mass, times 1 over molar mass, that answer, then we could decide what the limiting reactant is or is not. Okay. So We'll look at an example on page 313, practice problem number 1. Give you your reaction there. Which is the limiting reactant in this reaction when 0.750 moles of N2H4 is mixed with half a mole of peroxide? Well, first thing we should recognize right away is make sure the equation's balanced, and we see in this reaction there needs to be twice as much H2O2 as N2H4. They need to be in a 1:2 ratio. Well, they're not even close to being a 1:2 ratio. This says I need twice as much H2O2. It's not there. I don't even have equal amounts. So automatically, that's our limiting reactant. Okay. Now, let's just say we can do this. So let's go back and, for whatever reason, let's say you don't see that. Well, we can go back through and we can do a calculation to figure that out. So let's look here at what they're asking. In part A, which is the limiting reactant? That's easy, H2O2. Okay. How much of the excess reactant remains unchanged? Well, here's what we basically do is we say, all right, if I use up all of the H2O2, I'm only going to need half as much N2H4. Or think of this, do an A to B problem. If I have 0.500 moles of H2O2, I am only going to need 1 mole of N2H4 for every 2 moles of H2O2. I'm only going to need that much N2H4. Well, remember, if this is the excess reactant, this is all that's needed. 0.750 is available. 0.750 minus 0.250 equals 0.500 moles of N2H4 is left over, not being used. So that would be part B. Now, part C, how much of each product is formed? Well, that's easy. First of all, limiting reactant always determines the product. So what we're going to do is we're going to do an A to B problem, just like we do in section 9.2. The key you've got to remember here, limiting reactant always determines the product. Okay. If you look on page 314, okay, sample problem G, and here's one that they work out, and you can go through that. They start out with a mass of 2 reactants, and they want to know, obviously, what's the limiting reactant and things like that. So here's the first thing I do. You've got to change both of these to moles, then go through that calculation. So you should be able to see, going through that, how they work through that one and go from there. Okay. All right, so you can kind of work through this. Let's say we want to look, how can we do this a little bit quicker? Well, I'm just going to leave this phrase up here, and this is something you can do, and we can talk about it in class and things like that. But to do the shorter calculation, what you want to do is pick one of the reactants and call it chemical A. Doesn't matter which one. The other one you're going to call chemical B. And what you're going to do, and this is the hard part, you're going to ignore the amount of B that's given to you in the problem or question. Just ignore it. And what you're going to do is you're going to do an A to B problem. Okay. So you're going to, just like you would do in section 9.2. Now in section 9.2, okay, you do an A to B problem, mass to mass, whatever. Here's where a confusing piece comes in. We're not doing a new calculation, but here's what's confusing. Your answer is the actual amount of B that's used or needed. So with that answer, you're going to take the number that's given to you in the problem or the question. That's what's available. And you're going to compare it to what B, the amount of B that you found in the calculation. And you're going to ask yourself 2 questions. I've got a certain amount available. Is there too much B, or do I not have enough B based upon the calculation? And depending upon how you answer that question, you're going to know the answer to the limiting reactant and the excess reactant. Now, kind of gone through that quick, but I could sit here and go through a bunch of examples on the video, and it would take a long time. What I want you to do is on page 315, you got problem number 1 and number 2. I want you to show me these. Okay, show me problems using the longer method. And what we can do is talk in class about how you're working through those, and we can definitely do some more examples. All right, so that's the first part of this section, talking about limiting reactants and excess reactants.